Welcome to this explainer. All right, let's dive right into this high-stakes mission briefing. Today, we're taking a hyper-indulgent anomaly, what is honestly the absolute pinnacle of state fair engineering, the deep-fried peanut butter cup, and we are treating it with the grave scientific precision of an aerospace protocol. Because frankly, this isn't just baking. We are running an operation in extreme thermodynamics here, and the margin for error? It's razor thin.
To really understand our baseline problem, we have to look at the target itself. We're dealing with something made almost entirely of low melting point fats, specifically cocoa butter and peanut oil. Now, unlike water-based batters that can absorb and sort of deflect heat by letting off steam, these pure fats have virtually zero structural integrity against high temps. If you were to just leave these out at room temperature and then toss them into a deep fryer, the rapid heat transfer causes instantaneous disintegration, so this aggressive pre-thermal manipulation is absolutely required for survival.
The stakes for this whole operation are entirely binary. On one hand, you execute flawlessly, and you get the ultimate goal, this perfectly contained, lava-like molten core suspended right inside a crisp shell. But on the other side, well, we face our absolute failure state, a catastrophic, kitchen-ruining, localized blowout. There's literally no middle ground here, which is why sticking strictly to the protocol is absolutely mandatory.
So here's our laboratory protocol index, our agenda, detailing the exact phases we're going to execute today. We'll walk through protocols alpha, beta, gamma, and delta before we wrap up by thoroughly analyzing that blowout failure state, just so you know exactly what pitfalls to avoid.
Okay, let's move straight into protocol alpha, cryogenic stabilization. This is our critical foundation. Look, if you skip this phase and try to plunge a room-temperature peanut butter cup straight into hot oil, that chocolate is going to boil right through your batter in about 15 seconds flat, completely ruining both your dessert and your frying oil. So, pre-freezing is essential. And critically, you have to unwrap the standard-size cups first. Freezing them right in their original wrappers might sound like a super convenient time saver, but trust me, it is a trap. The expanding moisture during the freezing process actually freezes the paper directly to the chocolate, which completely compromises the whole operation when you try to peel it off later. Instead, just place them entirely bare on a parchment-lined plate or baking sheet.
And this number right here, 2 hours. This time frame is strictly non-negotiable. The cups have to be submerged in the freezer for a minimum of 2 hours because there is a massive thermodynamic difference between being merely cold and being cryogenically stabilized. They need to be rock solid to their absolute core. We are establishing a vital thermal timeline here, right? That frozen center is exactly what gives the cup the structural integrity it needs to survive the initial shock of the frying oil. Cutting this short is the absolute fastest route to a blowout.
So, with our core thoroughly stabilized, we initiate Protocol Beta, the encapsulation matrix. This is where we actually build our thermal shield.
Synthesizing our encapsulation compounds requires extreme precision. Now, if you look at the dry base, it relies heavily on double-acting baking powder. This gives us that crucial carbon dioxide expansion the literal second it hits the fryer, creating the lift and airy texture we need. Meanwhile, over on the wet emulsion side, you've got to vigorously whisk it to ensure a completely homogeneous bind. The whole objective here is to create a high-viscosity adhesion batter, something thick enough that it's going to cling perfectly to a smooth frozen chocolate surface without just, running right off the sides.
During the hydration phase, where you're actually pouring that wet emulsion into the dry base, you really have to whisk gently. Seriously, resist the urge to over-whisk. You're aiming for this highly viscous, almost sensory experience, kind of similar to folding a thick, heavy pancake batter. It should be rich, it should be slow-moving, and lumps are completely acceptable here. Actually, scratch that, they're expected. If you overmix it, you're going to aggressively develop the gluten network in the flour, which inevitably leaves you with a dense, chewy crust instead of that rigid, shatter-crisp thermal shield we absolutely need for the fry.
All right, now we reach the most critical and highly active phase of the explainer. Protocol Gamma, the thermodynamic execution, or as we usually call it, the fry. Your thermal medium has to be precisely calibrated. You need a heavy Dutch oven or a countertop deep fryer filled with about 3 inches of a neutral, high smoke point oil. Think peanut or canola oil. Why? Well, because using a low smoke point fat like butter or extra virgin olive oil at 375 degrees Fahrenheit, that's going to cause the oil to literally combust. It immediately breaks down the fat molecules and ruins the entire flavor profile with this awful, bitter, burnt taste. So, using a calibrated thermometer, you want to bring that neutral oil to exactly 375 degrees Fahrenheit, which is about 190 degrees Celsius. Your accuracy here dictates survival.
As you start the submersion, the protocol strictly dictates working in small batches of just 2 or 3 cups at a time. If you overload the hot oil with massive chunks of frozen mass, you're going to cause a drastic drop in the overall oil temperature, and that dooms the mission before it even really starts. Drop the frozen cups into your batter and use a fork to push them down to ensure absolute 100% encapsulation. Any exposed chocolate, literally any at all, is a catastrophic breach in your thermal shield that will instantly rupture the moment it hits the oil.
Executing what we call the drop requires really strict adherence to a simple 3-step sequence. First, you lift the battered matrix securely with a fork. Second, you let the excess batter drip back into the bowl for precisely 2 seconds. This ensures a uniform thickness right across the entire hull. And third, gently lower it into the hot oil. No splashing, no sudden movements. Nice and easy.
Now, from the exact moment of submersion, we are on a rigid timeline. Right at the 90-second to 2-minute mark, once the bottom achieves a gorgeous golden brown Maillard reaction, you know, that magical chemical process that rapidly reorganizes amino acids and sugars to create a crispy, incredibly flavorful crust, you execute the flip using a metal spider or some tongs. We have a strict 3 to 4 minute total window here. During this exact time frame, the exterior perfectly crisps up, while that frozen core gently thaws into that coveted lava state without breaching the crust.
With the payload successfully fried, we have to immediately execute Protocol Delta, safe extraction and serving.
When you pull the fried matrix out, place it directly onto a wire cooling rack set over a baking sheet. And guys, I cannot stress this enough, never ever use paper towels. If you do, all that aggressively escaping steam is going to condense directly against the paper towel. It traps the moisture and instantly turns your beautifully crafted, crispy bottom crust into a soggy, highly depressing paste. We absolutely need 360-degree airflow here.
These last steps finalize our entire objective. You want to aggressively dust the cups with powdered sugar while the exterior is still completely hot from the fry. That ensures maximum adhesion of the sugar to those residual surface oils. And finally, serve the payload within 5 minutes of extraction. Hitting this exact timing guarantees that the core is experienced in its absolute optimal, molten, free-flowing state.
But what happens if we ignore all these strict guidelines? Let's check the Red Team report and analyze the blowout failure state.
The absolute most common point of failure for home cooks attempting this is just sheer unchecked impatience. Maybe you only freeze the cubs for 30 minutes instead of 2 hours. Or maybe you crowd the pot and stubbornly let the oil temperature drop down to 325 degrees Fahrenheit. Because the oil is too cool, or the core isn't totally frozen, the frying process is forced to take way too long just to achieve that nice golden color. And if that batter matrix spends more than 4 minutes in the hot oil, this terrifying transition occurs. The chocolate core goes from molten to boiling. It will physically expand, violently rupture right through the protective batter shell, leak directly out into the hot oil, burn instantly, and create this acrid, hazardous smoke column right in the middle of your kitchen. It is a disaster. So, knowing that exact temperature control and the critical Phase 1 cryogenic patience are completely non-negotiable, I want to leave you with this final high-stakes question to ponder before you step into your kitchen. Do you have the patience to survive the fry? Follow the protocol, and I promise a perfect golden molten reward is waiting for you.